Uh, Thank you. So yes, it's me again, but this will be only 15 minutes. So yeah, okay, we will talk about dynamic optimization now, but before we talked about numerical optimization in the static case, where we have a fixed function, we should just find the optimal point. Of course, better to find the global optimal point. But in dynamic optimization, we have quite different goal. Okay, so this is the outline of my presentation. So let's start with discussing the idea of dynamic optimization. So as I said, our problem changes over time, so we will need to solve it online, and actually we need to track the position of the movement of the global optima, and not just find it. Many real dynamic optimization problems are, of course, black box, but this is the worst case scenario that we are considering. And the evolutionary computation methods are actually quite good for dynamic optimization because, well, the evolution itself considers some dynamics in the environment. So this is how we can state the dynamic optimization problem. So we have our function, which depends on the search space dimensionality, search space itself, time, and some set of environment parameters. So these are the values that change how the function performs. So where can we find dynamic optimization problems? So here you can see some list of possible cases where we can find this kind of problems. But as our first keynote today mentioned, also dynamic optimization, you can see that most of the optimal control problems are actually dynamic optimization problems, or can be formulated as dynamic optimization problems. And so, okay, you can ask, so what's the problem? Yeah, you can just take evolutionary algorithm because it is evolutionary, then it works with dynamic environments, and it will work fine. Well, yes and no. In some sense, it is possible, but the problem is, well, if the changes between environments are very the time of changes between environments is very small, so if the environments is changing very quickly, then we have a problem. So we will need to use our previous information about the search to search in the next environment. Probably most of the information would be useful. So for this purpose, several benchmark sets were designed with different location of components, size, shapes, rotation, number of optima, and so on and so on. So the latest modern benchmark to test difference approach to dynamic optimization is a generalized moving peaks benchmark. So it has some features like irregularity, asymmetry, ill cohesion, rotation. So on the bottom you can see how the main function looks, and on the right what kind of functions we can generate with GMPB. So yeah, those were simple cases, and these are more complicated cases, and this is only two-dimensional search space, and you can probably imagine how bad it looks in 10-dimensional, 20-dimensional, and so on. Okay, so for this work, I actually had to implement the GNPB myself in C++ because the original code was in MATLAB, and MATLAB is very slow and also difficult to connect to other algorithms. So you can actually download this benchmark, which is a repetition of our Australian colleagues that originally developed it. what are the methods that you could use for dynamic optimization problems? Well, there is one method, which is like shade for numerical optimization for static case, or L shade. There is this very simple mQSO algorithm, which is a PSO, particles one optimization, with quantum points and several other tweaks like exclusion and anti-convergence, like deleting bad swarms or deleting swarms that converge to the same peak, and so on. And also local search, which is one of the most important parts of mQSO. So, okay, where does genetic programming come into this story? So, as I said in my previous talk, we can design parts of the algorithm using genetic programming, especially in cases where we don't know how to make the algorithm better. And as I said, well, to create a new optimization method which is better than anything that existed before, well, this is a really hard problem. And it is also hard because we think about this as humans do. So maybe some human bias is present, and maybe there are solutions that no human would ever think about. Some non-trivial approach to optimization, for the dynamic optimization in this case. There is, of course, a drawback of such approach. It's computationally expensive. So for this idea, actually, I used the opt-to-push algorithm, which was proposed 5 years ago to generate local optimizers from scratch on the level of instructions. So here is the idea. The mQSO has a simple local search. You just take the best point and generate a point next to it, and if it's better, you just replace it. So the main idea is, let us generate a new, more complex local search with genetic programming. So the input is the best points. We sorted them by fitness, and the output is the new point that we need to evaluate and include in our population if it is better. So how does push genetic programming work? It has several stacks of instructions, like stacks of integer, float, Boolean, names, vectors, execution stack, and quite a lot of instructions that you can see on this slide. Like we can add, subtract, and so on. So here on this slide, it's a lot of text, I know, but this is how the solution evaluation in PushGP works. Actually, it runs an mQSO algorithm inside genetic programming just to evaluate one solution, and solution is a local search heuristic. So you can see it's shown with red that the first stages is we clear the stacks, we load our program, we load our set of points, and then we generate a new vector and replace it if it is better. So that's it. The rest is just to make it all work. So there are some evaluation criteria. So we use the first one, the best before change error, and made several tests. So here are the parameters of experiments. So there were 63 individuals in genetic programming and 40,000 generations. And it took 3 weeks to calculate on 4 computers in the network. So, and the MQ was a standard algorithm, and the problem parameters were varied just to eliminate overfitting. So as a result of 3 weeks of calculation, we got this code that you can see the upper part. And it's quite a lot of instructions, but if you simplify, it's actually only 4 instructions. 4, sorry, 4. We generate a normally distributed random value. We add it to the best point. We generate another random value, but not a vector, just one value. And we take a point between these two. So make a new point next to the best, and then search on the line between the second best and the best point. That's it. So how did it work? Well, the genetically improved mQSO actually performed better than the original mQSO. Of course, at the end of the test, we can see that the p-value is only 0.09, but if you look at the previous steps, like steps 99, 98, 97, it's more than the z score is more than 2 and sometimes more than 3. On the graph, it looks like this. So you can see that the green lines are mostly below the red lines, and especially the median, which is more important, actually. So as you can see, the generated heuristic actually works a little bit better than the original, and I didn't hear about such kind of local search before. Okay, it's very simple, yes, but if it works, why not? The idea of using two best points and searching along the line connecting, not them, but some point next to the best, well, it is somehow new and unusual, and this is what genetic programming does. It generates new heuristics for us that can work. So, well, of course, this approach can be used for other algorithms, and maybe this is something that we will try to do next. Okay, so thank you for your attention, and I'll be glad to answer questions.
Thank you very much for presentation. Any questions, colleagues, please? It was absolutely clear and understandable. No questions at all. Vladimir, how do you think can we transform these ideas to non-continuous space?
Yeah, of course, of course. Well,
For example, for combinatorial optimization.
Yeah, actually, well, most of the hyperheuristics are for combinatorial optimization, but I didn't have much experience with it. And as I looked in the literature, this is well developed area. So some local search in combinatorial space, there are some heuristic generated like papers from 10 years ago or something like this. But for binary search space, maybe.
Okay. Binary space usually is not so easy to transform.
Yes, for binary, it's more interesting to generate the whole genetic algorithm from zero, from scratch. But this is future plans.
Okay, I understand. Thank you very much. Any questions, please? No questions. Thank you very much again for presentation and answer my question. Now we invite for presentation Zakhar Novikov. Zakhar. Yeah, this is talk development of analysis of adaptive mutation in genetic algorithms.
Yes, thank you. Hello, everyone. My name is Novikov Zakhar, and I'm from Krasnoyarsk, from the Siberian Federal University. Today, I'm going to share our work on the development and analysis of adaptive mutation in genetic algorithms. Before diving into the specifics, let me explain the context of the problem. We are addressing a black box optimization. In these problems, we aim to find the minimum or maximum of a function, but we lack any prior information about its structural behavior. To make the task more practical, we transform this equality to an inequality, which means instead of finding an exact solution, we aim for an approximate one within an acceptable margin or year, which denoted here as epsilon. One way to tackle black box optimization problems is a genetic algorithm. Genetic algorithms are meta-heuristic methods inspired by natural evolution. They provide a powerful framework for searching through complex unknown solution spaces. On this slide, you can see a block scheme of the genetic algorithm. It starts with initialization of a population and followed by iterative processes like selection, crossover, and mutation. These steps simulate natural evolution to refine solutions and find an optimal or near optimal answer to answer over the generation. One of the key operators in genetic algorithm is a mutation. In this slide, I presented a classical mutation scheme, which works by randomly altering the value of one or more genes in chromosome, and the mutation probability is typically defined as 1 divided by a number of genes in the chromosome. Of course, there are many ways to define how the mutation works in algorithm, but this is one of the classical ones. And why we need mutation? It's needed to ensure that on average, at least one of the gene will mutate in each chromosome if we use this approach. And mutation helps introduce diversity into the population and prevents premature convergence by making random changes. It allows the algorithm to explore new areas of solution space and avoid getting stuck in local optima. So we set a hypothesis that adjusting the mutation rate based on population diversity can significantly improve and enhance the genetic algorithm's ability to explore solution space effectively. Because when the population diversity is low, it means that offspring generated through crossover are more likely to be similar to each other, as you can see on this scheme on this slide. In such cases, increasing the mutation rate can compensate for this reduced variability, helping the algorithm discover new solutions and avoid stagnation. So we developed a method that adapts mutation probability. First step of this method, in the first step, we calculate the probability of each position in the chromosome being a 1. This probability determined for each gene individually based on the overall population diversity. Not for each gene, but on each gene positions. So we would have a number of probabilities that equals to chromosome length. And on this slide, you can see a visual representation of how we calculate these probabilities for the first position. Next step is a transformation the position probabilities to ensure greater diversity in the population. The key idea is the closer position probability is to 0.5, the lower mutation probability should be. This is because the probability close to 0.5 indicates greater uncertainty and balance in the gene's value, meaning that gene is more likely to contribute to diversity naturally. On the other hand, if the probability is closer to 0 or 1, indicating low variability, the mutation probability should increase to maintain diversity and prevent stagnation. Additionally, this transformation ensures that mutation probability stays within a defined range between minimum and maximum mutation rate to balance exploration and stability of algorithm, so the mutation would not be equals to 0, for example, or 1. And on this slide, I draw the graphs to show how this function can work. On the first one, it's a linear transformation. On the second one, it's quadratic transformation. And This graphs shows the example of changing of these probabilities. First graph shows a change of position probability of one gene in one run, and second shows a linear transformation of it, which means the mutation for the gene, probability for the this gene. As can be seen, the closer position probability to 0.5, the lower the result mutation will be, and vice versa. The closer to the edges, 1 or 0, the higher the probability will be. We modified a little bit this method to try different algorithms that based on this. First one was a mutation probability calculated as the average of individual genes across the entire chromosome. This results in a single uniform mutation probability that was applied to all genes. Second approach was when mutation probabilities are scaled down over generation using a reduction factor. This gradual shift moves the probabilities toward a predefined target probability. The scaling is determined by the current generation relative to the total number of generations. Concurrent generations are more likely to use target probability. Another algorithm was a diversity-based method, in which mutation probabilities were adjusted based on changes in population diversity between generations. A scaling factor modified the mutation rates inversely to diversity levels. This means that when diversity is low, mutation rates are increased to maintain variation in population. And last one was when we dynamically adjust mutation probabilities throughout different phases of the algorithm. This strategy alternates between high and low mutation rates depending on the specific criteria or progress in the optimization process, and our criteria was a number of concurrent improvements. So we tested these methods on several benchmark functions. The error threshold was set to 0.01, and each function was evaluated in 10-dimensional space with 70 genes per chromosome. Each task was run 40 times to gather reliable results. And on this and the next slide presented results from our numerical experiments compared to the standard one. As can be seen, many results, but I can briefly say that they yield competitive results, but they don't consistently outperform the standard algorithm. And I can say the standard algorithm tends to show better results. However, they do help maintain diversity, as can be shown in the analysis of these methods. In these graphs, we created a graph that shows average pairwise Euclidean distance and average pairwise Hamming distance across 200 populations on the ACLI task with 2 dimensions. As can be seen, our modifications preserve higher diversity than the standard one across all the algorithm. Also, it can be seen from the distribution of solutions. This graph shows a distribution of the one run of this task actually with 2 dimensions, and on the left the standard algorithm distribution, and on the right modified. As can be seen, the modified one preserves higher diversity, and last graphs shows density map for the modified version, and it can be seen that it maintains diversity. So in conclusion, while the adaptive algorithm has not yet consistently surpassed the standard algorithm, it lays the foundation for more responsive approach. The algorithm's adaptability allows to improve exploration intensifying the search when trapped in local optima. It must be further improved to show better results while maintaining diversity. Thank you for your attention. I am now ready for any questions.
Thank you very much for your presentation. Dear colleagues, you have possibility to ask your questions. Well, it seems you're absolutely clear and everybody understands everything. Thank you very much for your presentation.
Thank you.
Dear colleagues, our next presenter is Anton Sopov. With the presentation Adaptive Component Crossover for Differential Evolution in Solving Single Objective Optimization Problems. You are welcome. Share your screen. Yeah.
Can you hear me?
Yeah.
Okay. Hello, my name is Anton Sopov. I am from Krasnoyarsk, exactly from the region of Siberian State University. The topic of my work is adaptive component crossover approach for differential evolution in solving single objective optimization problems. The presentation outline is presented on the screen. First, I will talk about the motivation of the study and why we have decided to implement this approach, about the problem statement of single objective bond constraint optimization, a brief talk about the differential evolution and crossover schemes, and then we'll go to the proposed approach and experimental results. First of all, many of the real-life engineering problems are presented as a black box model where the objective function is unknown, and therefore we cannot use the traditional mathematical methods. In this case, different heuristics and meta-heuristics are applied, and the evolutionary algorithms are considered as one of the most common and efficient methods for solving this kind of problems. For numerical optimization, the differential evolution has proved as one of the most successful evolutionary algorithms. Especially, it led to the development of the new and more efficient methods. The main operator of the differential evolution is mutation, although it usually uses two more operators. It is the crossover and selection operator. And while mutation and selection operators are highly discovered in many studies, the crossover operator is less discussed. And the popular adaptive schemes don't use any information about the search space variables and component, although it may affect the performance of the algorithm. The problem can be stated as the following way. We need to minimize an objective function, while the search space are all the numerical real numbers. We had a detailed tutorial about the differential evolution before, but to remind, it is a stochastic numerical optimization evolutionary algorithm, which main idea lies in difference-based mutation of random solutions. The classical version of differential evolution was presented by Storm and Price in 1995. It used the following mutation strategy, which is called round one. Of course, there are more many popular mutation strategy, but this is the most common. The crossover operator is the second in order operator in differential evolution, which is used to combine the mutant vector, which we have got before, with the vector in the current population. The most common scheme is a binomial crossover. If you worked with differential evolution before, you may have had noticed that the schemes are denoted as, for example, round 1 and the crossover scheme. Usually the bin. In this strategy, we have an operator which means crossover rate, CR, and if the randomly chosen value is lower than that, then we keep the current variable, and then we, keep the current variable as from mutate vector or keep it from the population. There are many another well-known strategies for crossover, for example, the exponential crossover, but the binomial scheme is the most used. In the recent differential evolution specification, for example, in the shade algorithm introduced in 2013, adaptation schemes were implemented. For example, the shade algorithm uses historical memory to keep the values of the crossover rate, which was successful, and then use it to generate the new values. But there is a problem that most of the popular and efficient schemes are not considering the variables of the solution space, because, for example, in the later studies of evolutionary processes, if, for example, every variable changes except for one was successful, then if the last one was unsuccessful, then the whole individual may be less fitted than the previous. And in order to keep the success of the crossover high, we have proposed a adaptive component crossover strategy, which calculates the objective function and variable changes during the process and tunes the parameter for each variable. The proposed strategy can be divided in the following steps, which we will discuss now. The first step is to calculate how each variable changed and affected on the whole individual. There we have a weighted change matrix. For example, if the individual changed slowly or didn't change at all, then it might not have influence on the overall change, and we should not consider it. But if it changed a lot, that it might make some influence on the overall change. And so that's the way how we calculate the weighted change matrix. So we take the projective function change, delta f, and multiply it with weight function, which looks like this. So if for example, if the change is low, near 0, then we give it a small weight. Or if it is high, then we give it more weight. These are two variants of implementing the weight function. Of course, it can be tuned, or it is possible to propose a completely new method. After we have calculated the change matrix, we should combine the mean values for each variable. We have proposed the following scheme. At the first stage of algorithm, the population diversity is higher, and there is not much the weights are not converged yet, so we give the current changes more weight. But later, when the algorithm converges, we should not change it much, because there are mostly unsuccessful changes of the individual. Then we normalize it to the interval. As the first stages, we give the variables the higher values of crossover rate, but later we lower it. And finally, when we have calculated our crossover rate values, we generate our crossover rates for each variable only for this iteration. So when we have proposed the scheme, we need to test its efficiency. We have used the CEC benchmark, the 22 year. We have proposed the scheme yet for the basic differential solution. So we compared it with the rand 1 binary scheme. The dimensionality for those problems was 20. We have calculated the best median, mean, and standard deviation values. There were 30 runs as in the rules of the competition. And differential solution settings were as following. In the table, the results are presented for each of the problems. As it can be seen, most of all, the proposed scheme, denoted as rand 1 ACO, was better on every problem except for the F1 and F6 problem. If comparing weight with the sign scheme to the weight with the step scheme, the sign scheme was a bit more stable and shows a better performance overall. Also, the mean and standard deviation values are presented on the table. We have compared the algorithms to the basic divergent evolution on the Wilcoxon rank sum test, and it showed that overall the proposed scheme had a bit better performance or equal, except for the problems that we mentioned, those F1 and F6. Next, to visualize the behavior of the algorithm, we have visualized the convergence of the algorithm. It can be seen that the proposed algorithms converges a little faster, except for the F1 and F6 problems. Also, we have visualized the number of successful crossover operations during the algorithm. On the x-axis, it is function evaluations or iterations, and the y-axis, we have the number of successful crossover rates, and it can be seen that at the later stages of evolution, the crossover rate increases, which means that the algorithm does not converge for a specific local optima and tries to find more solutions. But of course, that is not the case for F1 and F6 problems. So overall, in this study, we have proposed a novel crossover scheme, which have demonstrated the best or equal convergence spins and crossover success rate on most of the problems at the benchmark, except for the mentioned problems. We have implemented the generalization of the method, and we have compared to weighted function strategies. In the future work, we will try to implement following scheme to the state of art of differential evolution algorithms, or also we'll try to reduce the computation time of the algorithm. For example, try to somehow reanalyze the stages of the algorithm. And of course, we will try to expand the benchmark problems also, or try some real engineering problems and compare the scheme to the state-of-art algorithms. Thank you. I am ready to answer your questions.
Yes, thank you very much for your presentation. Unfortunately, you're out of time and we have no chance to ask questions. Maybe in personal contacts we will discuss it further. Thank you very much. Dear colleagues, our next presenter, Aleksandr Morshinin, Axiomatization of comatroids with girth functions. You are welcome.
Hi, everyone. Okay. My name is Aleksandr Morshinin. I'm from Omsk, Sopov Institute of Mathematics. I want to tell you about some theoretical results, but I hope everything would be clear. So let's start from the what is hereditary systems. First of all, we have an Y, U non-empty finite set, and A non-empty index family of subsets with we call it heredity or independence axiom, which means that if some set is in A, then every subset of this set is also in A, and we call the A independent subsets. And all other sets satisfies another axiom. We call that it upper hereditary axiom, which means that if some set is in D, then every superset of this set is also in D, and we call these subsets as dependent sets. We also interested into another sets, B it's a basis or maximum dependent subsets, and C it's cycles or minimal dependent sets. As you can see, if you know some of the index family A, B, C, or D, then you know all over indexed families. So that's why, from this point of view, every index family defines the one hereditary system. And for us, it's interesting to know about the fact that for every subset of U, we have a set of bases of this set. Basis, it's maximal independent subsets, which lies in the X, and we have for any subset, we have cycles of this subset, which is sets which includes X like a subset. So on the picture, you can see how it looks like. And it's very abstract, and I think more interesting to understand these things on the example. In general, these things came to us from the algebra, like linear dependent or independent vectors, from the graphs theory, from the graph theory, like independent sets of vertices in graph. But I want to give you an example of another hereditary system. For instance, we have some graph G, and a subset of vertices I is a vertex cover if for each edge, one or maybe both ends of this edge lies in the set I. So if it's true, then I is a cover set. It's easy to see that if some set of vertices is cover set, then every superset of this set is also a vertex cover. So the system H with V, it's a set of vertices, and D, it's a family of all vertex covers in this graph, is hereditary system. At the right, you can see I draw a little example of the graph with 3 vertices and 2 edges. I write all indexed family A, B, C, and D on the left. For us, interesting only D and C, and you can see that D is all vertex covers of this graph, and C, it's a minimal vertex graph, vertex covers of this graph. So this object is very close related with optimization problems. There are a lot of instances of optimization problems, but I want to consider the following. The goal is to optimize, the goal is to find some circle in some hereditary system which minimize some additive function. Additive function, it's a non-negative set function. A non-negative set function f is additive if it's monotonic, and for any partition of any set, this inequality holds. This equality means that it's equivalent of it's discrete equivalent of linear function. You can part your set on the different parts, calculate function from every part, and sum them. And this sum is equivalent to the value of function from all set. So this optimization problem is mathematical model of many optimization problems. And these problems are equivalent to the problem of finding of cycle of minimal weights in some hereditary system. For instance, as an example, let's consider this optimization problem, minimal vertex cover problem. We need to find the minimal vertex cover in a graph G. The example is the same. We have a graph with 3 vertices, 2 edges, and as you can see, the minimal vertex cover, it's the set which contains only 1 vertex, 3. And on the other side, this set which contains only vertex 3, it's a cycle of minimal weights in our hereditary system. We can say that weights of all vertices are equivalent to 1. So that's why we can find the cycle of minimal weight. And in general, I could say that, and as you said, as you know, this problem is NP-hard. One way to solve the problems, we have very simple algorithm which we call greedy, but I want to tell you about the reverse greedy algorithm, but it's very simple. It's very it's the same as a greedy algorithm. It's very popular algorithm because it's very simple, and because it's very simple. So what you should do, you at step 0, you should sort elements of your initial set in non-increasing order of weights, and initial solution, it is all elements of U, and on each steps we try to execute the vertex with index I from our current solution, and if we can execute the element and our solution is still independent, then we execute the vertex, the element. If we can't execute the element and our solution is still dependent, we don't execute it. So we do it for each vertex. We do it n steps, and in the end we have some solution which we have some solution, which in general, it's not optimal, but it's a good, good property of this algorithm that we also always find the feasible solution. I want to tell about one case of heredity systems. It's comatroids, and in heredity system is a comatroid if all circles of any V have an equivalent cardinality. From the other hand, we can say that comatroid is heredity system is comatroid when beside the first property axiom of heredity, we have another property that if we have two if we have two dependent sets and cardinality of one set is cardinality of second set plus one, then exists an element which lies in the difference of sets first and second sets. And from the first set we can exclude this element and it's still dependent. For instance, if we talk about the graph heredity system, it's a comatroid if and only if our graph is a cluster graph. A cluster graph, it's a graph each component of which is a clicker. And why comatroids is good? Because if we have an additive function, if we try to solve our optimization problem, then our reverse greedy algorithm always find the optimal solution. Here I draw example of graph with 5 vertices, 2 edges. All vertices have some weight. They are not equivalent. Here at the right I write all the cycles of this heredity system, and I want to show you how reverse greedy algorithm finds the optimal solution. First of all, we sorted our elements in non-increasing order, and then step by step try to execute elements from our initial solution. At the first step, our initial solution, it's all set U. And at the first step, we try to execute the vertex with index 2. We can execute it because all the vertices is still a cover set, vertex cover. And in the second step, we execute another, the vertex with index 3, and so on. On the last two steps, we have only 2 vertices, and we can't execute them from from our solution, because if we execute, for instance, vertex 1, vertex 4, the set which contains only vertex 4 doesn't form the cover set. So that's why on the last 2 steps, we don't execute vertices from our solution. And as you can easily check that our solution is an optimal solution for this problem. So that's why if our heredity system is comatroid, then reverse greedy algorithm always find the optimal solution for this problem, but only if our objective is additive function. So it's why, from this point of view, comatroid is an example of a good domain of function, since reverse greedy algorithm always find an optimal solution to problems with additive function. So we have a goal to be interested in study the properties of comatroids as a Boolean lattice on the set on this set with some given function. And an example of such function is girth function. What it means, if we have a comatroid, then a girth function defines as a function that maps for each subset of U a cardinality of this the cardinality of any set of X. Here you can see how it defines, and if And if our heredity system is comatroid, then the family of independent sets defined as follows. And the main result of my research is the next theorem, that if we have a comatroid, then the girth function have 3 properties for each x and y. This function is it's non-negative, and the value of this function is greater or equal to the cardinality of the set. This function is monotonic, and this function is supermodular. And the opposite, if we have some function which satisfies these 3 properties, then the set D defines with the equality 1 has a properties D1 and D2, and our system is comatroid. Why I speak about it? Because you can notice that if we have a comatroid, everything is okay. We have the algorithm that always find the optimal solution. But as I said, it always find the optimal solution to only to problems with additive objective. And for instance, if we have another function, for instance, submodular or supermodular, we don't have any algorithm which guarantee to find the optimal solution. So from this point of view, these properties could be used to find the some approximation algorithm. And for the case of hereditary system, we can also define the girth function and try to explain some properties of this function, and try to construct approximation algorithms. So it's like a first step to understand the heredity system from the point of view of girth function. So it's about plans, and I think that's all. Thank you for your attention, and I could answer any question.
Thank you very much for your presentation, but you also are out of time, unfortunately. That is why questions and discussions
No problem.
will be offline in interpersonal contacts. Thank you very
Thank
much.
you.